In this video, I want to take a look at the composition of matrix transformations. That is, I want to look at two transformations, let's say TA going from Rn to Rk and Tb going from Rk to Rm. Notice that this first one, the matrix A has to be K by N. The input is the number of columns. The dimension of the output is the number of rows here, so K by N. Likewise, B is M by K. So I'm starting here in Rn with some vector x. I apply the transformation TA to get to TA of x, and then that I'm going to apply TB to get TB of TA of x. And I want to look at what is the direct root, what is without stopping in between. What's the matrix that I need to do the composition of those two? Well, it's not too hard to guess what this is going to be. It's going to be the product of the two matrices. So if A is K by N and B is M by K, then the transformation, which is the composition of the two, is the same as the transformation of the product of the two matrices. And so multiply the two matrices together and use that as the matrix for a transformation. It'll be the same as this. Notice that matrix multiplication is not commutative. So what we're saying here is applying TA first and then TB. So when your inputs here are on this side, they get multiplied by A first and then by B. Okay. The proof is pretty straightforward just because of what the definitions of each of these transformations are, right? So to say TB of TA of x means this, TB in parentheses TA in parentheses x, and then A of x, TA of x means multiply A times x, TB of something, multiply that something by B, and then there's a property of matrix multiplication that is associative, so you got to keep the order the same, but you can change the grouping. But B times A times x is what we would do for the transformation T BA of x. So this transformation does exactly the same thing to x as that transformation, and there are equal transformations. Okay. We've noted above that the composition is not commutative, so we have to be careful that the composition in one direction may not be the same as the composition in the other direction. For instance, the transformation A is reflection across the line y equals x, and B is reflection across the x-axis, right? So the y coordinates become negative. If they were negative, they become positive. And so doing it in one order, so B times A is this matrix, and B times A, let's see, A was the blue one and B was the red one. So if I first do the blue one, so I'm just looking at a particular point here, 4, 2, reflect across the line y equals x, I get to 2, 4, and then reflect across the x-axis, I get down to 2, negative 4. But if I do it in the other order, if I do reflect across the x-axis first, that gets me from 4, 2 down to 4, negative 2, and then the other reflection gets me over to negative 2, 4. And you can see the difference in the matrix multiplication, where this is B times A, and this is A times B. Actually, they're close to the same, but one is minus the other. Yeah, one ends up down here at 2, negative 4, and one ends up here at negative 2, positive 4. So exactly the negative result in this case. Now, order makes a difference, but we can still say but we can still calculate what each one is. Now, there are a couple of situations where the order doesn't matter. For instance, rotations. I'm going to go down here. The composition of rotations. So A is the matrix for rotating through an angle of theta, and B is the matrix for rotating through an angle of phi. And my claim is that I can do this in either order. It makes some sense. If I take the plane and I rotate it through an angle of theta, and then I rotate it through an angle of phi, the total was theta plus phi. And if I rotate through phi first and then theta, it's still plus phi plus theta, which is the same as theta plus phi. So it doesn't really matter what order you do them in. And the proof looks, just try it. This is the matrix for the rotation through theta. This is the matrix through phi. If I multiply those two matrices together, it looks like this. So I'm doing B first and then A, right? Because when your inputs always come in on this side, they get multiplied by this matrix first and then that matrix. So I have, this was B and A, so you multiply them together. And so first row, first column, cosine theta cosine phi minus sine theta sine phi, that's this one. And then down here would be sine theta cosine phi plus cosine theta sine phi, that's this one. And then over here is this times that. So minus, there's a minus there. So minus cosine theta sine phi minus sine theta cos phi. And lastly, this and that. So minus sine theta sine phi plus cos theta cos phi. And now, how's your trig? Here's some identities. That this first one here is the cosine of theta plus phi. And the second one, factor minus sign out, this is minus the sine of theta plus phi. Actually, this one down here is the sine of theta plus phi. And this one over here, usually we write the cosines first to minus the sines there. This is the cosine of theta plus phi. That's this one and that one are the same. And so what I have here looks like a rotation matrix, right? The rotation matrices were all, the first column was cosine of an angle, sine of the same angle, and then second column minus the sine of that angle, cosine of that angle. That's exactly what I have here. The angle here is theta plus phi. Cosine theta plus phi, sine theta plus phi, minus sine theta plus phi, cosine theta plus phi. So this is rotation through an angle of theta plus phi. Now, addition is commutative, so I could switch the order of these now and do cosine of phi plus theta, and then work my way backwards and say, okay, then this would turn into this with all my phi's turned into thetas, which would turn into this with all my phi's turned into thetas, and the reverse, and I'd end up with B times A. And so they are, in this case, commutative, and the net result is you rotate by the sum of the angles. That would be what we'd hope, and sure enough, the matrices and the trig identities all make that line up, right? Now, reflections, on the other hand, are not commutative, as we saw up here, right? We saw that doing these reflections, starting here, going down and up, or going up and down, we end up in different places. However, there is something we can say about those reflections. And the reflections are, composition of two reflections is a rotation. So what I want to look at is one line here. Let's give that angle, oops, let's grab this. Let's give this angle theta, and this angle all the way up there phi. And I want to look at reflection across both of them. So if I have a starting point here and I reflect it across the blue, would get me about to there, and then reflect across the red would get me over to here, right? So the net result is this spot went to this one. Of course, doing it in the other order, I'd get a different result. But if I did it in the other order, this point reflecting across the red line first would end up, clear over here, and then you reflect that across the blue line, and you'd end up, down here somewhere. So certainly reflecting across the blue and then reflecting across the red is different than reflecting across the red and the blue. Okay. But I claim that there is something I can say. I claim that this is a rotation. So here we go. Here's the matrix proof of that. So A is going to be my matrix for reflecting across the blue line, and we saw in a previous video that the reflection matrices looked like this. If you knew this angle, then cos 2 theta, sine 2 theta minus cos 2 theta would be the matrix I need. And so B being the red line here, reflection across that, it looks the same but with phi's in there. I'm doing BA. So I'm doing the red, I'm doing the blue one first, doing across this, and then across the red one. So here we go. This is B, this is A, and I just multiply them together. And I get first row, first column, so cosine 2 phi, cosine 2 theta, plus sine 2 phi, sine 2 theta, and so on. Just do those out. Again, how's your trig? Do you recognize identities? Cosine, cosine, plus sine, sine. That's going to be the cosine of a difference of those two angles. Cosine of 2 phi minus 2 theta. It's also the cosine of 2 theta minus 2 phi that really multiplication is commutative here and here, so it's hard to say which one should come first in this subtraction. But cosine is an cosine is an even function, so it doesn't matter. You can the cosine is symmetric about the y-axis, so you can take this side or that side, you get the same results. So it doesn't matter here. This one, on the other hand, sine is odd, and the order does matter. And the way I think of this is this minus sign, I could slide it into here, into this sign, and it would become negative. So I had a plus out here with a negative in there. But then I could throw a negative, so the negative goes with the phi, and then I can just throw a minus sign into that one because it's cosine and it's even. And so this becomes the sine of 2 theta minus 2 phi. The minus sign went with the phi. Okay. Down here, it's the other way around because the minus sign is going to flip into this sign as a minus, giving it a plus sign out there. So this is the sine of 2 phi minus 2 theta. And lastly, this one right here is the cosine of 2 phi minus 2 theta. The only one that's different here, we got 2 phi minus 2 thetas. This one is 2 theta minus 2 phi. But again, I can slide the minus sign out of that and change the signs of everything inside. And I end up with the cosine of 2 times phi minus theta, the sine of 2 times phi minus theta. This looks like rotation through an angle of phi minus theta. No, 2 phi, 2 times phi minus theta. So looking back up here at my original, well, no, 2 examples here. Rotation here, whatever this angle, this is phi minus theta. And so the rotation from here out to there, that rotation is twice whatever this is. If you look at the example I did up above with the 2 rotations, no, the 2 reflections, one of the angles was 0 and the other was pi over 4. So the difference is pi over 4, and double that is pi over 2. So my claim is that it was rotation through an angle of pi over 2. Notice in this order, when I do the red one first and then the blue one, this was rotation that way through an angle of, that's a 90 degree, that's a right angle, so that was an angle of twice pi over 4 or pi over 2. Doing it in the other, doing the blue first and then the red, this was a rotation going that way, and this rotation was through an angle of minus pi over 2, right? The difference this time would have been 0 minus pi over 4. So the difference is minus pi over 4, and you double that, it's minus pi over 2, and the rotation is that way. So even though it makes a difference which way you go when you do, which order you do those reflections in, it's still a rotation after you do 2 reflections. An interesting example is when your 2 reflections are perpendicular to each other, like the x and y axis. If you reflect over the x-axis, then you reflect over the y-axis. That's exactly the same thing as a half turn, or a turn of pi. So you can flip things over by, well, you can flip things over without changing the orientation, rotate them over by doing 2 reflections with perpendicular axes. Okay. This is something you see sometimes in a bathroom when they've got mirrors on 2 perpendicular walls. So you got these walls here, both of them have a mirror on them right here and right there. And what happens is you see yourself back here. You're standing over here looking at yourself that way, and you see yourself standing back here looking back at you. The thing is, though, what you're seeing back there is a reflection off this mirror, off that mirror, and then coming back to you. So you're seeing a double reflection of yourself. If you ever find yourself in this situation again, raise a hand and see which hand goes up. It might surprise you, because if you just looked into this mirror over here at yourself right over there, and you raised the hand on this side, well, the hand on this side would come up. But when you're looking at this double reflection, when you raise your hand on this side, this one will come up, because it will be the reflected image. This one is the reflected image of you, and that one is the reflected image of this one, which ends up being the same hand. So it's really odd to see that reflected image of you raise the wrong hand, or at least the one you're not expecting it to raise. Okay? Because it's two reflections, it's a rotation. Anyway, there you go. There's some composition of matrix transformations in R2.